First off, we have this thing called the extreme value theorem. Extreme value theorem. Okay. And what it says is that if you have a function and it's on a closed interval, then and if f is continuous, then what happens? You're guaranteed there exists a max and there exists a min. Right? There exists a max and there exists a min. So whenever you have a continuous function on a closed interval, then you're guaranteed to have there's gonna be some place where a max occurs, and there's gonna be some place where a min occurs. Okay. And how do we find it? This is basically what we know at this point. We know how to find the maxes and mins for a continuous function on a closed interval, right? So how do you find it? How does one find them? How does one find them? Well, we play this game of Fermat's theorem, right? Fermat's theorem says the only places they could be, or Fermat's theorem implies, say, that the only places they can occur are where one, either the derivative equals 0, or 2, the derivative is not defined. F prime equals 0, or f prime is not defined. Right, and that could include endpoints. Okay, so at this point, this is basically our only strategy, right? Somebody gives you a function and says, where is this function a max? Where is this function a max? The only thing you can do at this point is say, well, I'm going to check where the derivative is 0, I'm going to check where the derivative is not defined, and I'm going to check at the endpoints. And those are the only places where the extrema could be, and I know that one of them is going to be the max. So let's look at the values at each one, right? Let's look at the values at each one. So in this picture, you'd say, I'm going to look where, let me make a function that's a little funny. I'm going to look where the function has a derivative of 0. I'm going to look where the derivative is not defined. And I'm going to look at the endpoints. Right? So I've got these 4 possible places. These are the only places that the max or min could be. And if I'm looking for the max, all I need to do is just evaluate. Right? And I'll evaluate the value of the function at each point. And I'll say, oh, this is the biggest one. This must be the max. Because the max could only be at one of these 4 places. And this is the biggest value. Right, so this is going to be the max, and then this one would be the min, where the derivative, this point where the derivative doesn't exist, that's where the min is attained. Okay, so that's basically what we've been doing up until this point, stated concisely. Okay, so this is sort of a crude way of doing things, and we have something a little bit better. So there are better ways. Or more sophisticated ways. To determine there are more sophisticated ways, and they start off with an observation. Okay. They start off with an observation. So here it is. Okay. Suppose you have a function, and you know that the derivative is positive on an open interval. I. So you have this function, it's on an open interval, let's call it open interval I, and we know that the derivative is positive there. Okay. Then, what am I going to say? What do you think I'm going to say about the function?
Is it continuous?
It's continuous. Well, certainly you know that if a function's differentiable, then it's going to be continuous. That's true. But we have something a little bit better. It's not just differentiable, but its derivative is always positive, right? Can you say anything? Can you say anything about the? Can you say anything about it?
Sorry.
Yeah, go ahead.
Does that mean it's increasing?
Does that mean it's increasing? Yeah. Yeah. Why do you say that?
Because does that mean f of b is greater than f of a?
Yeah. So you're saying this is going to be a mean value theorem, some implication of the mean value theorem. So then, so like mean value theorem comes to mind. You know that f is increasing. Great. Then I should give you a bonus point on the exam. Fine. So that's pretty good. Okay. So the function is increasing, and the way you see it, the reason why you know that is the mean value theorem, right? You say, well, look, increasing means that. So if you pick any 2 points, right? So why do we know this? Why do we know this? Well, pick any 2 points, A and B, where A is smaller than B. Okay. Here they are. They're inside of I. So I'd like everybody. So Gwyneth knows what's going on. I'd like everybody to think, just for 20 seconds or so, why does the mean value theorem tell you that f of b has to be bigger than f of a? Then the mean value theorem tells you that f of b has to be bigger than f of a. Whoops. F of b has to be bigger than f of a. Okay, so I'd like you to think about it just for half a minute. Why is that? Why does the mean value theorem tell you that? As a person, it's my natural tendency to look kind of scary. Like, why does the mean value theorem tell you that? Like this. So I always have to remind myself, no, look encouraging. If you go through the videos, no doubt you'll see this transformation. Almost every class. Like. Okay, talk to the person next to you. Talk to the person next to you.
It's just like the general because I don't know. What did you guys think?
They would be on the side. Yeah, but like at time, just oh, like it's like for D, like right here now. Okay, that's greater than F.
Okay, who has anything to say? Does anybody have anything to say? Sarah, go ahead.
Well, so since the mean value theorem like gives you the slope like between
Yeah.
f of a and f of b.
Yeah.
If it's positive, then it's increasing.
Yeah. So that's exactly right. Right. The mean value theorem says at some point in here, you're going to have a point where the slope at that point equals the slope of the line between the endpoints. But you know that the derivative, right? So there's some point where the derivative has the same value as the slope between the endpoints.
Which is greater.
But you know that this thing is positive, and so that slope must be positive, and so one is greater than the other. So let's state it a little bit more precisely. The mean value theorem says there exists a C between A and B where f prime z equals f of b minus f of a over b minus a. Right? There's a place where the instantaneous slope equals the slope of the line between the endpoints a and b. There's some point where that slope equals the slope. But we know we are given that f prime is positive everywhere. So f of b minus f of a over b minus a is positive. Right? And so f of b minus f of a must be positive. Right? Because b minus a is positive. B minus a is positive. So you have if we multiply on both sides by that, we get that f of b minus f of a is some positive number times a positive number. In other words, f of b is bigger than f of a. Okay, good. And that's exactly the right intuition. Okay, and then this is how you would write it down. But even if you wrote down that intuition, that's the bulk of it right there. If you understood that intuition, this is sort of the formal writing of math. Okay. Any questions? Any questions? Okay, and you can say something similar for decreasing function. So similarly for decreasing, right? If f prime is less than 0 on the whole interval, then f is a decreasing function. Okay, so let's see how we use this in the finding of maxes and mins. Okay, so let's consider the function f of x, x cubed plus 3x squared minus 45x plus 2. Okay, on the whole line, on all of the real line. Okay. So first off, how do we find where the extrema might be? Where are possible places for extrema? Where? First question, right? So our problem is, find the extrema. Find the extrema. So where are extrema possible? Where are they possible? Somebody said it.
Derivative 0.
Where the derivative is 0, right? So just evaluate f prime. So it's going to be 3x squared plus 6x minus 45. That's 3x squared plus 2x minus 15. That's 3x plus 5, x minus 3. Right. So the only possible places, only at -5 and 3. Right. Okay. Everyone should be okay right up until this point. Okay. So now let's ask where is f increasing and where is f decreasing? Using the previous statement. Okay. So we need to find out what do we need to do? We need to find where. What do we need to do? Maybe somebody who hasn't seen this stuff before. If we want to find out where f is increasing, well, one thing we can do is look at the look at the derivative and find out where it's positive. Right? So here's the derivative. Right? How do you find out where it's positive and where it's negative? Does anyone remember how to do this? This is sort of a pre-calculus. This is something you learn in pre-calculus, and it seems almost useless at the time. Now it has a use. Now that skill has a use. So you say, okay, well, I know where this guy is 0, right? This function is going to be 0 at 3, right? If I look at the graph of this function, right, it crosses the x-axis at -5 and crosses at 3, right? Yeah.
Can you just pick points between -5 and 3, greater than 3, and less than -5? See whether they're positive or negative.
That's right. That's right. So one way to do it, you may remember this, is that if it's a polynomial, it's either going to be all positive or it's going to be all negative between the zeros, right? So for polynomials, between zeros, the function doesn't change sign, has a constant sign. Right? So one way of doing it is you can just pick points and evaluate them and see what the sign is. So we say, okay, let's put in a 0 here, and what do we get? Well, we get 3 times 5 times -3, so that's something negative. Right? So we know that the function is, we know that f prime is negative here. And then over here, what is it going to be? Well, you choose like 10 million, right? And you get 3 times something huge times something huge. That's definitely going to be positive. Right? And over here, you choose something gigantic, hugely negative, right? And what do you get? Positive, right? Because you get 3 times a negative number times a negative number. So this one's positive here. That's one way of figuring out where this polynomial is positive or negative. Another way would be just to say, well, look at this thing. It's a quadratic. It's a parabola, right? And it's an upwards parabola because the lead coefficient is positive. So I know what it looks like, right? It looks like this. So I know it's going to be positive, negative, and positive again. Okay. So you just remember what parabolae look like. Okay. In any case, that tells us where. F, the original function f, is increasing before -5, decreasing after -5, and before 3, and increasing after 3. Okay, so what does that tell you? Our possible extrema, they're extrema possible only at -5 and 3. And we know that the function's increasing before -5 and decreasing after -5. So what do we know about -5? It's a max, right? It's a max. So we know -5 is a local max, right? Because f prime was positive before and negative after, so f is increasing before and positive after, right? This is the graph of f prime, remember. The graph of f will look different. Right? What we know is that the graph is increasing here and then decreasing here. Right? This is the graph of f. And it decreases all the way down till we reach -3. And at -3, after -3, it turns around and becomes increasing. Okay. So what does that tell you about -3? Well, I mean about 3, excuse me. 3 is going to be a local min. And 3 is a local min. Okay. So, so this is, this is maybe a more sophisticated way of identifying what you found, right? Previously, all we could say was that, well, if there are extrema, they occur at these points. And now what we can say is that, in fact, we can figure out that, in fact, there are extrema at these points, and we can tell what kind they are. Okay. So this is a classification. This is like it gives you the ability to figure out what you found. Okay. Does that make sense? So let me sort of write what we just did down. Let me sort of codify what we just looked at. So this thing is called the first derivative test. So you have some function f. It's differentiable on an open interval. Okay. And suppose that f prime c equals 0. If f prime is less than 0 for x less than c and bigger than 0 for x bigger than c, then, well, it's going to be decreasing and then increasing, so c is a local min. C is a local min. If f prime of x is bigger before and less after, then it's going to be a local max. And if f prime doesn't change sign, then it's neither min nor max. It's okay? Is it okay, visitors?
What does C say?
Where?
C.
What is C?
And I mean, as in ABC, what is
Oh,
C say?
if f prime doesn't change sign, then it's neither min nor max, right? Because that would mean that, if it was 0 here, but you were increasing before and you were increasing after, right? So you're not or it could mean that you were decreasing before and you're decreasing after, right? Well, then you're not a min or a max.
Wait, so the x's that you plug in are like the 10 million and the negative 1 million?
Well, this is a little bit, I've sort of written it a little bit sloppily. So really, when I say for x less than c, what I mean is that for x in an interval to the left of c. So when I say this, what I really mean is for x in c minus delta comma c. So here is c, where the derivative is 0. If in some half interval here, your derivative is negative, and in some half interval on the other side, your derivative is positive, then you're going to be a local min. Okay. So yeah, when I wrote it, I felt like that's a little bit imprecise because you don't need It doesn't have to be for all x less than c. That's
Okay.
definitely not true. It just needs to be in some half interval.
Okay.
So, so that's what I mean when I say for x less than c. I really mean in some small interval, some small half interval to the left of c, and some small interval ending at c. Okay, so this is good, right? The derivative gives you some way of gives you a way of determining what kind of if you found a max or min among those things that you're looking at. So okay, let me make you do one. Okay, so try this. Yeah, I'll put up two. So here's one. Yeah, I'll just put one. X squared e to the minus x on the whole line. I'd like you to try to find any maxima or minima for this function. Okay. So take say 2 minutes and see what you can get. I'm going to put up another one also. X squared natural log x. So also try that one. okay, turn to somebody next to you and talk for a minute. Say what you're getting.
Oh, yeah. Okay, yeah. Okay. Well, around the zero, I got
That's a 0?
Yeah.
I gotta change it.
Okay, wait, did you plug in like 1? Okay, no, you're right. I mixed it up.
Yeah, wait, is it? Did you guys get into look at?
0 is the min?
Yeah.
And 2 is the min.
Yeah.
Okay, sorry.
I didn't actually like finish this.
I again only got 0.
Okay, would anybody like to say anything? I should say that I didn't specify the domain of this thing, but what is the domain? What is the domain? What should the domain be? All real numbers? How? 0 to infinity, right? Because the natural log isn't defined for 0 or over 4. Okay, so let's go back to this one. So what do? Anyone want to lay it out? Go ahead, Victor.
So you keep the derivative, which using the product rule would be 2x e to the negative x minus x squared e to the negative x.
Is everyone okay with that? Okay, good.
And then you turn that into x e negative x times 2 minus x, and you get the roots 0 and 2.
Great. Okay. So you factored out the x e to the negative x out of both terms. You get a 2 minus x left. Great. So roots at 0, 2. Okay. And then
I picked 1, 3, and negative 1,
Okay.
and just plugged them into the derivative.
Okay, so you evaluated, right? You have this thing, e to the negative x times 2x minus x squared. Right, you plugged in points and you evaluated, what did you get?
I got that it was positive between 0 and 2 and negative at the right.
Mm-hmm. Okay, so you could do it by evaluation, or you could do it by saying, well, look, this thing is a parabola again, right? This part is a parabola, so you know that it's going like this, right? And you're multiplying this parabola by e to the minus x. E to the minus x is that positive or negative?
It's just 1 over, so it's positive.
1 over x, 1 over e to the x. E to the x is always positive, right? E to the minus x is also always positive, right? So you're taking a parabola and multiplying it by something that's always positive. So that's not going to change the sign. So you know that it's 0, negative plus negative again. Okay. Either way you want to do it. Okay. So, and that gives it to you, right? So it says that, 0 is a min, local min. And 2 is local max. Okay. Oops, I just erased it. Okay. What about for this one? Somebody else want to try? Should I roll another? Where's my 20-sided die? I lost it. I hate this. 5. Wait. It's actually I should just forgo rolling the die.
That's hilarious.
Yes.
Okay, I use the product rule again.
Yeah. So you take the derivative, you get what?
The 2x ln x
Mhm.
plus x squared, well, plus x.
Yeah. X squared 1 over x. Right, so 2x ln x.
And then you can
X.
factor out the x if you would like. So you have x parentheses 1 plus x ln x.
You have you have x times 2 ln x plus 1.
Oh, yeah.
right? So where is that equal to 0? That could be equal to 0 when, the only way you can get 0 is if one of the factors is 0. So either x is 0, right? So so this has zeros at x equals 0, or this equals 0, right? Right. So looking at the second one, right, natural log of x equals -½ right? So what's x? Anybody? E to the -½ right? 1 over the square root of e. Right? Okay, and we also have this other root, right, where x is 0, but the function isn't defined there, right? That was a possible root because of the x squared thing, but the function isn't even defined there, so we can't use this one. Right? That's not a root. Okay. So there's only one place for the root. Okay, and let me I'll just finish it up for you since we're running a little bit over time. So there's only one place for the root, 1 over the square root of e. So 1 over the square root of e. And then if you think about this function, the natural log function, right? The natural log function is going to be this is basically like the natural log function multiplied by a positive number. Okay, so again, that doesn't change the sign. So you're going to be negative before, and you're going to be positive after. Okay. So what does that give you? The original function is decreasing before and increasing after. Right. So e to the -½ is a local number.
How did you get that it's a local then?
Because it's decreasing, this is f prime, and f prime is decreasing before. I'm sorry, f prime is negative before, so the function itself is decreasing before.
Oh, I see.
Right?
Okay.
F prime is positive after, so the function is increasing after.
Now I understand.
Right? So it's got to be a local thing. Okay. Okay, that's it for today.